On 9th of September, we, the batch of 1969 IIT Kharagpur, met together at Pleasanton in the Bay Area, and we visited the Computer History Museum. The Computer History Museum was one of the finest museums that probably tells you about the history of computers starting from the 50s, early 50s to 2000s and till today. The host, Amitabh Mukherjee, senior to us from IIT Kharagpur, was the docent, and he took us through a very wonderful journey. I'm just giving a few clips of the visit that should interest the viewers to go and have a look at that museum. Thank you.
History has shown us that we've gone through 3 industrial revolutions. Now, who can tell me in the 18th century what was the first discovery that spurred the first industrial revolution?
Steam.
Who said something?
Steam.
Steam.
Steam
Correct.
engine.
Steam. Everything was running by steam. Inside the houses, the factory, steam. James Watt, remember? James Watt. In steam, industrial revolution. Who can tell me what was the main invention that spurred the second industrial revolution in the late 19th century?
Electric
Car. Oil. Somebody said electricity. That's correct, exactly. Thomas Edison and company. Okay, so the third industrial revolution had started during the Second World War. And that was the first time that we started keeping information digitally, we recorded digitally, we analyzed digitally, and we presented our results digitally. And that was the beginning of the digital revolution, and that is what this exhibition is all about. The big theme of this tour is, and this question will come up at the end, so please pay attention, innovation is an evolutionary process, so that it's like a relay race. One runner hands it over to the next goes on, and some of these leaps are incremental in nature, others are giant leaps. And you put all these incremental leaps together, and what you get is a revolution. That's why the story begins. There's always a problem, remember? What is the problem now? So, in the 1890s, late 19th century, people were immigrating to the United States, especially from Europe. And the United States Constitution requires us to take a census. Typically, I would ask the crowd, why do we take a census? I don't have to ask this crowd. Obviously, it's because how many representatives will represent your community is proportional to the population of that group, of that community. So, in the meantime, we didn't know how many people lived in the country. So how are we going to do that? So at that time, here is a survey form, literally a survey form, and they used to go from door to door and farm to farm asking questions like, where did you immigrate from? How many children do you have? What is your profession? Etc. And literally go back to their offices and tabulate by hand. Can you imagine how inefficient that process would be? So, as a result, it took more than 8 years to complete the census operation in the country. It was almost counterproductive because it was time for the next census again, and they couldn't use the data. So they said, we need a better process. That was the problem. So young Herman Hollerith, with the top hat, 20-something years old, he used to work in the Census Bureau. So he said, I have a suggestion to improve the process. I said, what's your suggestion? He said, when I go on the trams or the trains in the East Coast, the conductor comes and punches my ticket. You remember they did that in buses in India. Punches your ticket. Why are you punching my ticket? I said, sir, the story goes that they're trying to understand the physical characteristics of the passenger, but there's more to it. What time of day was it? Where did you get onto the train? How far are you going? Did you get a chance to sit down? And with this data and information, we can reorganize and optimize our operation. It'll be certainly beneficial for us. It'll be comfortable for you. So he said, what a brilliant idea. He said, we already have the data on the survey forms. So what we're going to do is we're going to transcribe the data into punch cards. Punch cards like this. 24 columns, 12 rows, and he invented this pantograph machine that you see here. So you put the card in there and you punch holes based on the data that you collected on the form. And so essentially you've transcribed the data and described the demographic details of almost every individual in punch card form. You put the card on the tray here in the spring-loaded lever mechanism, and what you can't see there is there are pins under the platform. Yes, there are pins. And so when you lower the lever, wherever there's a hole, the pin would go through the hole and touch a pool of mercury. What happens when you touch a pool of mercury? Huh? What?
You get poison.
Exactly, you complete a circuit, electrical circuit. So wherever that circuit is completed, the corresponding dial moves up by one. And so you have a running tabulation of the data that you collected. And so periodically, people would go up and take the data from the tabulation there, and about 5,000 cards could be done in a day by one individual. And so that was a big step forward. And by the way, not only that, you could ask analytical question, data analysis. How many women above 40 are school teachers? This is sort of sorting through the data. Corresponding cartridge would come up on the other side, and you can put the card in there and then count the cards later. So you get data analysis, which is a big deal today. It's all about data, not so much about computers. Anyhow, so this was a big benefit, big invention. So Faida kya hua? So he said, Faida is that the entire process was reduced to 8 months. Now you got the benefit. Now they could really use the data for not only to get the number of representatives, but for other government purposes. So Herman Hollerith formed this company, Hollerith Census Company. Phone rang off the hook. He got orders from the government, and he was very successful. And so what happens when you have a very successful company? People want to come and join your company as soon as possible. Who was one of the first ones to step in?
IBM, Watson.
Tom Watson Sr., exactly right. Tom, he was a brash young sales guy, very, very ambitious. He was there taking orders, I don't know if they had phones at the time, but the almost phone rang off the hook. He took orders, he also got wealthy and successful. But Watson's mentality and attitude was quite different from young Herman. Herman was calm, collected, conciliatory. Watson was just the opposite. Brash, very ambitious, and wanted his way. And so he had a great idea. Hollerith, he said, Tigay, I have the maximum number of shares in the company. If you do well, I automatically do well. Why should I worry about the day-to-day operations? You take care of this. You take care of the company, and I'm going to sail into the sunset. Which is exactly what he did. Became a millionaire in, I'm talking about 1890s now, 1900.
Yeah.
I mean, that was a lot of money. Now over here in Silicon Valley, you can't even get a cup of coffee for $1 million. So Hollerith disappeared, and after some mergers and acquisitions with this Hollerith Census Company, ultimately this became IBM. Beginning of IBM with Tom Watson Sr. as the CEO and president in the year 1924. So next year is actually the centenary of IBM, right? Yeah, exactly right. And so what you're looking at is the beginning of IBM here. Now, rhetorically speaking, is this the first time that they thought of punched card format to collect data and operation? No.
Because textile mills.
Exactly right. And by the way, if it was, I wouldn't be asking the question. If it Anyway, let's take a giant leap into the Second World War. And the United States has now joined the Allies in the war, and they're supplying arms and ammunition like we're doing now for Ukraine. But there was a problem. There's always a problem to be solved. What is the problem now? The problem is that the infantry and the people on the battlefield are saying, we don't know at what angle to place our guns for the shells to be effective. There are so many variables. The enemy position, the weather, the terrain, the shells themselves. Each of these, for you all, it's probably just walk in the park. Each of these is actually a partial differential equation. Each of these, and you have to solve them simultaneously in order to come up, given these conditions, what should the angle be? So, the Department of the Army, U.S. Army, had a request for proposal. He said, we need a handbook in the field so we can quickly look up and say, okay, this should be 15 degrees, or that should be 45. So I said, who can provide us with a solution? So Presper Eckert and John Walkley were two professors of electrical engineering in the University of Pennsylvania. They said, we propose to build the ENIAC, Electrical Numerical Integrator, and Computer, ENIAC. And what you see here is the mock-up of the ENIAC. It's like a 3-bedroom apartment, 100 feet by 80 feet, or weighs about 30 tons, and you can see people working inside the computer. Now we carry a supercomputer in our pocket, and there are ladies and people with miles of wires inside the computer. By the way, the ladies with themselves were called computers at that time. And of course, there are banks of switches, miles of wires, and it was little unwieldy to work with. And before I forget, remember the theme of the tour was innovation is an evolutionary process. This 3-bedroom apartment got reduced to one little chip by 2 graduate students in the University of Pennsylvania in 1990. But anyway, I digress over here. And so, but there was always a problem. Now there was a fundamental problem with operating this computer. What could that be? I should have mentioned actually that there are 17,468 vacuum tubes.
Oh,
I gave the story away. The vacuum tube is the problem. The filament in the vacuum tube, as soon as you keep turning it on and off, thousands of times, the filament burns out. And even one vacuum tube burning out, your answer is not reliable.
Right.
But anyway, he used to run around with new vacuum tubes, guessing which one will burn out. But it's hard to guess. There are so many vacuum tubes, which one is going to not operate, and you have to replace it. But they got the problem solved finally to make it operational. But when they finally got it done, it was November 1945. What's wrong with that date?
Time distance. Oh, wow.
The war was over. It never got used for the purpose that it was built. But it did serve as a proof of concept that given a very difficult mathematical situation, you can use something like this to solve your problem. And this, by the way, later on was used for the Manhattan Project and for other Defense Department projects. It finally got moved to Bethesda, Maryland, their proving ground, Army's proving ground, and one bright day, it, of all things, got struck by lightning. It was almost like a divine intervention, saying, you've had enough with this, please move on. But before I move on, I want to ask you another question, since you're not asking me questions.
I'm going to ask you.
Now I'm going to ask you a question. There are 4 fundamental properties of a modern electronic digital computer. It has to be electronic, yes. There's a vacuum tube, it's electronic, all right. It has to be digital, yes, it was counting. 1, 2, 3, 4, 5, 6, 7, it was counting. Each time you turn it on and off, it's a count. It has to be general purpose. Okay, you solved a problem related to the Defense Department. Tomorrow you can rewire based on the logic and you can solve a financial problem. Okay, general purpose. What is the 4th fundamental property of a modern digital electronic computer? And you use it every day, all the time.
Portable.
Portable, no. This was not exactly portable,
Oh, yeah.
but we have portable. But a fundamental property,
Electricity.
it has to be binary.
Yeah.
Only 0 and 1.
Yeah.
Everything that you see on your computer screen, on your iPhone with Lata Mangeshkar singing, and you standing in the front of the Eiffel Tower, all of that behind is a whole bunch of zeros and ones. Imagine all of that coming together so that you can see your pretty pictures. Imagine the advances we've made. But ENIAC was decimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It has to do with set theory, number theory. It counted in tens. Base 10, remember? Logarithmic, base E. This was base 10. And everything that we do now is base 2. Remember that because I'll show you when we come to logic circuit why 1 and 0 are so important. So they said finally, okay, who owns the intellectual rights to this invention? Professor said we designed it. University said we housed it. Army said we paid for it. And the lawyers, like all the time, they had a heyday. The professor said, okay, time out. We don't need you. Keep your computer. We are going to go off and design it ourselves. So the professor said, okay, we'll still stay in Philadelphia, but we will form our Eckert-Motley Computer Company. And everything what you see here is exactly the ENIAC, except they call it Universal Automatic Computer, UNIVAC. And you see the front end of the UNIVAC here, and behind is the 3-bedroom apartment with all the vacuum tubes. And so, and before I forget, here is the mercury delayed storage device. Imagine, just in simple terms, waves of mercury flowing. When it's at the peak, it's a 1. And when it's in the trough, it's a 0. So you're counting ones and zeros by movement of waves of mercury. Imagine, and it had a very small minimum amount of local memory. At any rate, the whole idea then was, rather than be so academic and only Defense Department problems, let's open it up so that companies can use it and make it more universal. That was their objective. And so General Electric Corporation, GE, was the first commercial company to give them the order. And at that time, now you're talking about in the mid-50s, aerospace was beginning to grow. Boeing in Seattle, Lockheed Martin just down the road here in Sunnyvale, and Lockheed Martin in Los Angeles. No, sorry, McDonnell Douglas, Northrop, McDonnell Douglas. They're all designing planes, etc. You need to do heavy-duty calculations. They used UNIVAC, and most of all, NASA was just born and was beginning to grow. And then they have these rockets in the nose cone of a rocket, even for intercontinental ballistic missiles. Guess what the nose cone has? All the telemetry and the guidance data. Nothing but a supercomputer sitting on top of the nose cone. And you have to be able to, from remotely, you can actually. Anyway, so Tom Watson, now his son, actually Tom Watson Jr., right here, he was equally ambitious and he equally wants to be the top of the computer industry. And he's saying, everyone's talking about UNIVAC and nobody's really paying attention to IBM. Our business plan is wrong. We need to change the whole company. And so he said, what I'm going to do is I'm going to sequester some of the best engineers in the company and a few good business people too in upstate New York. I don't exactly know where they did this, but somewhere up in a swanky hotel in upstate New York. I said, you debate the whole issue out amongst yourselves and then come and advise me how I should reorganize the whole company. And they did that. We'll get into the details a little bit, but the result was IBM 360 and it's System 360. In other words, some of the things they suggested was, rather than have silos of equipment, CPU here, storage there, archiving over here, all sort of incompatible with each other. Sometimes software ran on this computer but didn't run on that. So the salespeople complain, we don't know how to sell. It may or may not work, and people don't want to take the risk. So he said, okay, let's streamline the whole thing. It's like a factory, like a chemical engineers in the crowd, you'll understand, petroleum refinery. Raw material is coming in, go fast, just 35 minutes. Okay, so that was fine with the mainframe and fairly expensive for large corporations. That was great. but the marketplace was demanding, give a smaller computer, something more affordable, so small businesses could use it, and maybe departments and major universities could use a computer themselves. So what you see here is a mini computer. And this is from Digital Equipment Corporation. Somebody asked about DEC earlier. So there it is, PDP-8, PDP-8. The advantage about this was, of course, it was electronic, but the advantage was, while the program is running, you can actually stop the 1947. 1947, some of the best places, best place to work for engineers, scientists, physics, chemistry, mathematics, all branches of engineering was where? Murray Hill, AT&T Bell Labs. Exactly. It started in Manhattan on the west side, but soon moved to Murray Hill, New Jersey. And amongst many other things that were invented in AT&T Bell Labs, here is something got invented which has changed our lives forever. This is a transistor. What does the transistor do? Transistor turns on, turns off, it can amplify signals. Essentially, it does the same thing that our good old clunky vacuum tube did. Turn off, and also amplify signals. Except this was not reliable. It was burnt out and much bigger. And in this case here, nothing burnt out. And if you work on it, it gets smaller every year. So you can put more and more transistors in your circuit. If you have a circuit board like this, instead of putting clunky vacuum tubes here, you put little transistors. And since they're getting smaller, you can make it even more complicated. This is a very simple diagram of a circuit board. Anyway, the main thing is that William Shockley, John Bardeen, and Walter Brattain got Nobel Prize in Physics for the invention of the transistor. And deservedly so. This has changed. In spite of being a Nobel laureate, was paranoid. He didn't have the self-confidence that he is recognized as a leader, as a great scientist. He was constantly worried, is my name going to be on the paper? Am I getting credit? Is my picture on the newspaper? Now, these are things that scientists don't need to worry at all. You already are a Nobel laureate. But it goes back to the way he was brought up in his childhood, etc. I don't have time to get into that. So Shockley didn't get along very well with the people he worked with in AT&T Bell Labs. His superiors actually encouraged him to see, can you find alternate employment somewhere else? Nobel laureate. So anyway, he picked his bags and his knowledge, and he said, okay, I'll teach them how to do something with the transistor. And he moved lock, stock, and barrel. Where did he move to? Right across the street over here, Mountain View, California, just on the other side of Route 101. And he's Shockley Semiconductor Corporation. And of course, he hired some of the best young PhDs in computer science, Bob Noyce, Gordon Moore, John Henry, and some of you might recognize Eugene Kleiner of Kleiner Perkins, venture capital. And these guys are getting smaller every year as they're doing more research. Then comes the tyranny of numbers. There's always a problem. The problem is, how do I connect all these little guys together and make it reproducible in a factory? Because over here now, what you're getting is into a semiconductor, a chip, a microprocessor. But there are lots of connections to be made. That was called the tyranny of numbers. So Shockley and company worked on this, except Shockley again was very paranoid and didn't treat his bright young PhD scientists carefully at all. And they were all upset. They said, we don't need this kind of ham-fisted management. We can work on our own. So it turned out that 8 of them, the traitorous 8, they're called, including Bob Noyce and Gordon Moore and the names I mentioned, they spun off. But before that, Shockley Semiconductor Corporation actually got the funding from Beckman instruments. Some of us used Beckman instruments in our experiments. Beckman actually funded the work, funded the formation of the Shockley Semiconductor Company, but they needed seed funding when they spun off these traitorous eight, and now venture capital is a big deal in the Valley and around the world. Where did it all start? Arthur Rock was a guy who used to work in Wall Street. He came over and he said, okay, I'll put you in touch with Sherman Fairchild. Who was Sherman Fairchild? Sherman Fairchild was a brash, young, debonair from Los Angeles, and Fairchild is a photography company. And their expertise was in cameras and remote sensors and things of that child. And Sherman also, by the way, Sherman was, his father was one of the co-founders of IBM. And Sherman had one of the largest share of IBM shares. And he said, no problem. He said, I'll invest. And Arthur Rock put the two together, and that was one of the first venture capital work that was done in Silicon Valley. And by the way, even before that, there was venture capital in East Coast, in New York. And the word was not venture, adventure capital. So you wonder, why did venture capital come from? It's adventure capital. Rockefellers, Bixby's and others invested in smaller companies who couldn't get bank loans to start their business. Anyway, so Arthur Rock put the two together and they formed Fairchild Semiconductor. It was one of the most successful chip-making companies. And somebody asked me, how did Silicon Valley start? How did Silicon Valley start?
Thank you very
Fairchild
much. Was there at that time.
Fairchild Semiconductor Corporation. And then later on, I'm jumping the gun here, Fair Children were formed. After the traitorous eight, some of the people peeled off on their own later on to form Variant Associates, form Teledyne. And this was also, again, with help from Arthur Rock to put the money together. And small companies started sprouting in the Valley. And this became very popular. Anyway, so make a long story short here quickly, Jack Kilby also in Texas Instruments was trying to solve the same problem, tyranny of numbers. Turns out, to make a long story short, Kilby wrote his paper about how to produce microchips or semiconductors before Bob Noyce and company and Fairchild published their paper in 59 January. He published it in 58 December. And as a result of that, Kilby got the Nobel Prize for Physics for the invention of the microprocessor. And it turns out, Nobel Prizes are given only to living human beings. Bob Noyce had just passed away from cancer.
You put this in process check 15 minutes.
Yeah, we need to speed up. Yeah. So, but Kilby always recognized Bob Noyce's work. He said, he deserves it as much as I do. But to quickly move on, all of this is fine and dandy. It all works lovely. But what is the fundamental, still the roots of how all of this works? George Boole, Boolean logic. He had the mathematical construct that allowed all this mathematics. We're talking to step back a little bit. All of this mathematics, how to translate that into something that you can do physically. And Claude Shannon from MIT actually used this logic to show that you can use either vacuum tubes or transistors to transcribe mathematical equations and make them do something on a circuit board. And or not, as something came up from George Boole. And gate. This is 2 years. It finally, I think, came up to in 65. And there's Gordon. He just passed away this year in Hawaii. And that is Gordon Moore's law. These not propeller heads, these copier heads in Rochester are doing nothing with this. They should be the king of the computer industry. He said, that's okay, don't worry. Then he quoted Picasso. Picasso said, good artists copy other artists' ideas and paintings. But some of the best artists manual to know what should I do next. It should be intuitive. Next step, yeah, you do this. And so he said, okay, please design. So you see what we've got. We got drop-down menus with simple English instructions. You should know, based on the application you're using, what to do next.